Hello, good morning, dear. Welcome back. Uh, this is lecture number 10, and we are discussing about the in a formal way, we are discussing the gradient descent algorithm and basically the three variants of gradient descent algorithm. As you know, gradient descent algorithm is the heart of machine learning optimization technique. And in machine learning model, for example, our linear regression model, we have one objective function. We call it cost function, and there has to be a optimizer. By the way, so in new term you have learned gradient descent algorithm also is called an optimizer. GDA is an optimizer. Why? Because it optimizes the cost function, and as a result of which the parameters are obtained. Okay. First, we will discuss about batch gradient descent algorithm. Sometimes it is also called vanilla gradient descent algorithm. The algorithm works like this. The Wj is a parameter which is assigned with xj feature. So, Wj assigned value equals to earlier Wj minus alpha times 1 by m summation of I equals to 1 to m, and this is our this is the derivative of our cost function. Okay. This is the derivative of the cost function, and alpha is the learning rate, This is also called hyperparameter, alpha hyperparameter. So, why it is called hyperparameter? Because it is controlling the parameters. Okay. Normally it is kept between 0 to 1 value, and depending on your application, it could be 0.01, 0.001, etc., etc. And detail we actually in my earlier lecture I discussed. It is hyperparameter because it is controlling how much by how much amount Wj will be compensated and how fast Wj will converge. Okay, that means now we are writing in individual form. Suppose there are n number of features, and with n number of features I have n plus 1. It is starting from 0. 0 is the actually W0 is a bias, and as you know, x0 is a fictitious feature whose value is always 1. That's why we are keeping it separately. Okay. So, as we have discussed that if there are n plus 1 number of features, there will be n plus 1 number of parameters, and this all the parameters within this loop has to be updated. Okay, and this is the updation rule, and this is actually the way it works. Okay, so what you are seeing here, say if m is very large, m is very large. Okay, say 40 million. Okay, and say n is also very large, n is a feature is also very large, say several thousand. Okay, maybe 1,000 or bigger. Okay. So, in that scenario, and what scenario can be thought of with this kind of size? Say we have in India 1.3 billion people, and suppose we are having some consensus. Okay, so where all kind of data is collected from door to door, and maybe millions of people's data are being collected, their age, their mortality, their income. So these are feature actually, and millions are different from the different parts of the country. Data has to be collected, and then suppose we are running machine learning algorithm to figure out the important information which is there in the data. So in that scenario, you can imagine that M is very large, and when M is large, then this you see how the upgradation rule is being executed. For one step, the algorithm in the contour plot we have shown, this is a contour plot. So here we have shown with two parameters that how this is goal and how the algorithm is moving. Okay. So very steadily and but very slowly it will go to the destination. Why slowly? Because for every step, to make a step, okay, that means to assign new value to Wj, the algorithm is scanning all the samples. Okay. So if you have millions of samples, then it has to scan millions of samples before taking a step, before calculating this parameter. Okay. So that's a problem, isn't it? Huh? So if n is large, so that's why when you should use this thing, we will discuss that when m is very large, you should not use batch gradient descent algorithm because it is slow. And if I plot JW versus the cost function, okay, then you will see very smoothly iteration after iteration, it should its value should decrease. Okay, with parameters W, its value should decrease because we are talking about the convex function. Okay, if you remember in our linear regression, the cost function is convex in nature, convex in nature, and that is it has a global optima, and Wj will actually converge to this value. Okay, and it should not change afterwards. Okay, and W parameters also how to monitor we have already discussed, but the basic issue here you have noticed that it is very slow but steady. You see, this is my goal, and if say m is reasonable, okay, say m size is sample size is less than say 5000 or so, then easily we can use batch gradient descent algorithm, and this is the way it works. But as I told that if the sample size is very large, then we devised another gradient descent algorithm which is called stochastic gradient descent algorithm, which is very common because in deep learning era we are talking of millions of parameters and billions of data. Okay, so n is very large, and your machine will hang if you try to determine your parameter using batch gradient descent algorithm. So here what essentially we do, we first randomly sample the training samples. Okay, you sample randomly all the training samples, and then for you are executing a for loop where this is your upgradation rule, where this is alpha is learning rate, and this is your derivative of the cost function. Okay, so this is really this is the derivative of the cost function. So if you see, you can notice here there is no summation. So what the algorithm is doing for every sample, so whimsically anywhere, because you are stochastically actually randomly suppling them. So, it is taking any value, okay, and then taking a decision, taking a step. Every sample it scanned and it just modify the parameter. So, that is the reason you see because you never know that you have not explored the other samples. So, you never know that you have gone in right direction or not. So, that is why there are oscillations in the learning process. So, if this is my goal, then this is my goal, and then it oscillates. Okay, the learning oscillates. That's the problem, and it will never converge with that precision with which your batch gradient addition converged, because of the very nature of the algorithm, the updation. Okay, but advantage is very fast. Sometimes 1 to 10 iterations it converge, parameters converge very fast, okay, because of this upgradation rule, okay, and randomly supplying the training sample. Because of these two reasons, it converges very fast, although may not be that the parameter value may not be that precise, but for many applications that is okay. Okay, so you can just keep a learning rate. If it is oscillating too much, you can play around with the learning rate. Okay, show that oscillation will be little less, but then allow the parameters to converge. And if you draw the cost function actually with W, then you will see some oscillation, but the trend should be like this. It should decrease. Why? Because again it is a convex function. Okay, very nature of the function will assure that it will actually converge, although there will be some oscillation. So, there is no free lunch in machine learning. The advantage of this stochastic gradient addition algorithm is very fast, because of this reason that it is taking decision about compensation of the parameter after every sample. Okay, and then if you can afford to sacrifice a little bit of precise values of W's, then this is the best option which you have. Okay, very popular stochastic gradient addition algorithm is. So, having said that, you have now seen batch gradient addition and stochastic gradient addition. Each has some advantage, disadvantage. So, taking advantage of both the algorithms, a new variation of gradient addition algorithm has been formulated, which is called mini batch gradient descent algorithm. So, idea is very simple. Here you create a batch size B. Okay, suppose I have huge samples, millions, but we have to create a batch size B and allow that batch size to be taken randomly. So, again you supple. Okay, so suppose you have batch sizes. Okay, say B is equal to some 1024, and you have millions of samples. So, every 1000 will consider as one batch and will consider as a sample otherwise in stochastic gradient addition algorithm. So, this batch actually is taken together, okay, and treated just like as if it is a one sample, and then run the algorithm like this. For batch size I equals to 1 to B, okay, then the parameter actually is upgraded, Wj is assigned Wj, earlier Wj minus alpha by B, summation of I equals to 1 to B. This is my again the derivative of the function. Okay, so this is how the algorithm is working. So, here you see this B is in your hand, whether you will take 1000 or say 512 or 256. Okay, you see I am writing this as a power of 2, okay, because this are to be executed in computer, and then computer memory has a size. So normally so this is a 1 2 3 4 bit register, we call that register, okay, or memory. Nowadays computers have 16 32 64 bit, okay, more than that. So it is if you have a GPU say with 1024, that's why these are the bit size, so that the batch can be kept at a time within that register, right. So that's why we select not whimsically any number, but try to select to the power something like 16, 32, 64, 128, 256. So this will be actually faster, that's the reason. So once you select batch, then you run this algorithm. Okay, this is just like vanilla gradient descent algorithm. Okay, and then the only difference is the B is again an hyperparameter. Okay, B hyperparameter, and you will have to judiciously based on your application, you will have to judiciously select the batch size. So what is the advantage here? The advantage is very obvious, that since B is within our control, we are not allowing machine to go slow, but at the same time some precise decision it is taking. So it is scanning batch wise, whatever samples are there in the batch, it will scan and then upgrade the parameter, okay, take a step. Okay, so I try to show here, this is a control plot again, control plot where you can see that the way it is converging much better than stochastic gradient descent algorithm, but again it is very fast, because the batch size, if properly tuned and if you can vectorize it properly, then it will really work very good, fast as well as precise. Okay, so it retains some precision of batch or vanilla gradient descent algorithms characteristics, and also it retains from speed perspective the gradient descent algorithms, stochastic gradient descent algorithms characteristic feature. So that is the story of mini batch gradient descent algorithm. And if you see, if I draw the cost function characteristic when iteration is going on, then as W will converge, there will be some oscillation, but oscillation is bounded. Okay, oscillation is bounded, and there is a good pattern that the oscillation, although it's oscillating, but it is decreasing. Okay, and batch gradient descent has wide application. Okay, and if properly vectorized, it almost always works much better than stochastic gradient descent algorithm. Okay, and almost it is as precise as batch or vanilla gradient descent algorithm. So that's the reason it is widely used in machine learning and deep learning paradigm as an optimizer, as a good optimizer. Okay. So here we can actually compare between the three variants of gradient descent algorithm. You see, this is again contour plot. We are plotting this, and you can see this is your batch gradient descent algorithm, this is mini batch gradient descent algorithm, and this is your stochastic gradient descent algorithm. The way it will perform has been depicted with a schematic diagram. This is your goal. Okay. So now the question arises that in which case what algorithm should be used. they are application specific. If possible, if your machine permits, if your application permits, go for batch or vanilla gradation algorithm because of the precision. Okay. Say if you have sample size 1000, 2000, 3000, maybe 4000, up to 5000, you can easily go, and n is not very large. In that scenario, you can go for batch gradation algorithm, and if they are crossing the range of millions, okay, then of course you need to go for stochastic gradation algorithm. Okay. And if they are really large, and if you can do a good job in dividing the sample space into batches, okay, and then you judiciously determine the batch size, then of course mini batch will be preferred than stochastic gradation algorithm. It's a good competitor, and mostly it outperforms stochastic gradation algorithm. So, but here, as I said, that there are hyperparameters. Alpha is the learning rate, and there is another hyperparameter which is b, that is the batch size, which you will have to determine as an expert or as a having some domain knowledge. If you can do that, then mini batch gradation algorithm will really work much better. So with this, I would like to conclude, and I would like to tell you that afterwards also, those who will study deep learning, you will see that there are many variations of mini batch and then adding momentum term. The objective is precise and be fast. Okay. So many more variants of gradation algorithm will study, but for machine learning, these three you should practice. You should do the assignments now using these three variations of gradation algorithm. With this, I wish you all the best. Stay safe. Bye bye.